Hello, this is Tony speaking. In the beginning of our video, I want to show you a game in my cell phone. It's called Ship in Dream. So it's about ship. And here it is. Let's check it out. So the game was created for people who cannot sleep in night so that they can count sheep. You can download this if you want. It's CD and easy. So 1, 2, 3, 4, 5. No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that might be a bit hard, so let's make it easier for me. It's another day, but where is the ship? Where is the ship? 1. Come on. 2. One more. One more, please. 3. So you can see if I play this game for infinite days, I can get infinite ship. So our topic today is infinite geometric series. An example which is called Zeno Dichotomy Paradox.
This is Zeno of Elea, an ancient Greek philosopher famous for inventing a number of paradoxes, arguments that seem logical but whose conclusion is absurd or contradictory. For more than 2,000 years, Zeno's mind-bending riddles have inspired mathematicians and philosophers to better understand the nature of infinity. One of the best known of Zeno's problems is called the Dichotomy Paradox, which means the paradox of cutting in two in ancient Greek. It goes something like this. After a long day of sitting around thinking, Zeno decides to walk from his house to the park. The fresh air clears his mind and helps him think better. In order to get to the park, he first has to get halfway to the park. This portion of his journey takes some finite amount of time. Once he gets to the halfway point, he needs to walk half the remaining distance. Again, this takes a finite amount of time. Once he gets there, he still needs to walk half the distance that's left, which takes another finite amount of time. This happens again and again and again. You can see that we can keep going like this forever, dividing whatever distance is left into smaller and smaller pieces, each of which takes some finite time to traverse. So, how long does it take Zeno to get to the park? Well, to find out, we need to add the times of each of the pieces of the journey. The problem is, there are infinitely many of these finite-sized pieces. So, shouldn't the total time be infinity? This argument, by the way, is completely general. It says that traveling from any location to any other location should take an infinite amount of time. In other words, it says that all motion is impossible. This conclusion is clearly absurd, but where's the flaw in the logic? To resolve the paradox, it helps to turn the story into a math problem. Let's suppose that Zeno's house is 1 mile from the park, and that Zeno walks at 1 mile per hour. Common sense tells us that the time for the journey should be 1 hour. But let's look at things from Zeno's point of view and divide up the journey into pieces. The first half of the journey takes half an hour. The next part takes quarter of an hour. The third part takes an eighth of an hour, and so on. Summing up all these times, we get a series that looks like this. Now, Zeno might say, since there are infinitely many terms on the right-hand side of the equation, and each individual term is finite, the sum should equal infinity, right? This is the problem with Zeno's argument. As mathematicians have since realized, it is possible to add up infinitely many finite-sized terms and still get a finite answer. How, you ask?
So now we are going to learn the infinite geometric series. There are two kinds of infinite geometric series. The first one is Convergent Series and the second one is the Divergent Series. Let's talk about the Convergent Series first. Here is the first example. Consider the series 4 plus 2 plus 0.5 plus 0.25, etc. Then we can get a function y equals 4 times bracket 1 minus 0.5x squared over 1 minus 0.5. After using the calculator, we can get these two graphs and know the value of this function are closing to 8. In conclusion, as the number of terms increase, the sequence of partial sum approaches a fixed value of 8. So the definition of convergent series is a series with an infinite number of terms in which the sequences of partial sums approaches a fixed value. Next is the divergent series. We also have an example of divergent series. Consider the series 4 plus 8 plus 16 plus 32, etc. Then we get a function y equals 4 times bracket 1 minus 2x squared over 1 minus 2. After using the calculator, we can get these two graphs and know the value of this function continue to grow. As the number of terms increase, the sum continue grow and does not approach a fixed number. We can get the definition of divergent series is a series with an infinite number of terms in which the sequence of partial sums does not approach a fixed value. Can you get it? Yeah.
After knowing the definition of convergent and divergent series, consider the formula for the sum of geometric series from section 1.4, which is Sn equal T1 multiplied bracket 1 minus r n squared over 1 minus r. As n gets very large, for the values of r between -1 and 1, Rn squared approaches 0, and you can verify it through graphing calculator. Since Rn squared approaches 0, we got this formula, and we can replace Rn squared in this formula with 0, as you can see below. And eventually, we got the answer. The formula looks like this. Dun 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 dun! Here we show it again. This new formula, S equal to T1 over 1 minus R when R is between -1 and 1, can be used to determine the sum of an infinite geometric series. However, remember that it can only be applied to convergent geometric series.
Here's our example. There's a big square and 1 over 4 of the area is shaded. Assume the shading continues indefinitely in the indicated manner. So for the largest shaded area is 1 over 4, and then 1 over 4 of the quarter shaded area represents 1 over 16 of the whole square, and then the next shaded area represents 1 over 64 of the square. And then move our cards here. Let's go for our question 1. What is the series of terms that will represent this situation? Easy one, right? And our term 1 is 1 over 4, term 2 is 1 over 16, and term 3 is 1 over 64. And it continues constantly. So let's move to our second question. What is the sum of the shaded area? Do you remember the formula that we had mentioned? Dang dang! Yeah. Yes, you are correct. And let me fill in the blank. So S equal to T1 over 1 minus R. And R in our question is 1 over 4. So S equals to 1 over 4 over 1 minus 1 over 4. And finally, we got the answer. Dang! It's 1 over 3. Yay! So do we complete finishing the question? No. Don't forget to write the answer in a complete sentence. Da 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 da.